Welcome to Spring LIB.
So in this question, we have three wave functions that we need to check if they satisfy the wave equation here. Now, the velocity of the wave, as we can see, most of the wave functions are given in terms of the wave number and the angular frequency. Therefore, we can write the speed of the wave as omega divided by k. So this is the speed of the wave. So once we find the second spatial derivative and the second time derivative for the wave function, we just need to plug in the velocity here or the speed of the wave here, and then we can check if this wave function is satisfying the wave equation or not. Now, first of all, let's start by finding the spatial derivative for this wave function. So the spatial derivative is equal to minus a k sine kx plus omega t. Here we use the chain rule, and from this, if we derive this again, we'll get the second spatial derivative, and it's equal to minus a kx squared multiplied by cosine kx plus omega t, which is equal to minus k squared y of x and t, which is the original wave function. Next, let's find the time derivative. So partial y, partial x, partial t is equal to minus a omega sine kx plus omega t. And if we derive this again, we'll get the second time derivative, which is equal to minus a omega squared cosine kx plus omega t, which is again the original wave function multiplied by negative omega squared. Now, if we take this quantity here and multiply it with 1 over v squared, what we will get is minus omega squared y, x, and t multiplied by k squared divided by omega squared. These two terms will cancel, and we will get minus k squared y, x, and t, which is equal to the second spatial derivative. So we can say this wave function satisfies the wave equation. The second wave function we have here is y of x and t equal to a sine kx plus omega t. And we'll start again by finding the spatial derivative. So partial y, partial x is equal to k a cosine kx plus omega t. And from this, the second derivative is minus k squared a sine kx plus omega t, which is equal to minus k squared y, x, and t. So this is again the original wave function. The time derivative is partial y, partial t is equal to omega a cosine kx plus omega t. And from this, we can find the second time derivative, and it is equal to minus omega squared a sine kx plus omega t, which is again is equal to the wave function, the original wave function multiplied by negative omega squared. So y of k and x. Now, we'll take the second derivative of the time and do the same procedure to check if we will have the same thing, which is the value of the second spatial derivative. So partial the second partial derivative of the wave function with respect to time multiplied by 1 over the velocity square is nothing but negative omega y of k and x multiplied by k square divided by omega square. While these two will cancel, this will leave us with negative k y of x and t, which is the value of the second special derivative. So we conclude that this wave function also satisfies the wave equation. The last wave function we have is y of x and t equal to a cosine kx plus cosine omega t. Now we'll start by finding the spatial derivative again. So partial y over partial x equal to a, won't change, multiplied by minus k sine kx plus 0. And this will leave us with minus ka sine kx. The second derivative is partial. The second derivative here is partial square y partial x square equal to minus k square a cosine k cosine k x. So this is the second special derivative. The first time derivative, partial y partial t, is equal to a. Now the first part here doesn't depend on time, so it's 0 plus, because we have here cosine, when we derive it, it will be negative omega sine omega t, and this is equal to minus omega a sine omega t. Now we can find the second time derivative. So the second time derivative is minus omega square a cosine omega t. And as we can see in both cases here, we did not end up with the original wave function as the previous two equations, or as the previous two wave functions, but we still, however, can investigate if they satisfy the wave function or the wave equation or not by multiplying partial y over partial t. So the second derivative of the wave function multiplied by the square, or 1 over the square of the velocity. And that's equal minus omega square a cosine omega t multiplied by k square over omega square. If we cancel these two together, we'll end up with negative k square a cosine omega t. Now, at the first look, these two might, this function might looks like it satisfies the wave equation, but notice here the argument of the cosine function is omega t. However, in the second special derivative, it's kx. So this doesn't equal to the second spatial derivative of the wave function. So it doesn't equal to, and therefore this function doesn't satisfy the wave equation. So it's not a wave. Now the last part of this question, which is part D, is asking us to find the velocity or the speed and the acceleration for the second wave function in part B. It's just easy. We will take the time derivative. We just need to find the time derivative, the first and the second. So the first time derivative for the wave function is this. Let me choose green here. So this is the first time derivative. And as we know, the definition of the velocity is it's the first time derivative of this space or the position. So here to find the transverse velocity, we just need to find the first time derivative. And the second time derivative, of course, will give us the acceleration. So the second time derivative will give us the acceleration for this wave function, the transverse acceleration.